Greetings, my name is Bruce Hemp, Applications Section Leader with Analog Devices. Today we're going to look at a reference design for an IQ demodulator signal chain with industry-leading 1 GHz bandwidth. This compact, high-performance design directly supports complex demodulation of RF signals with a carrier frequency range up to 9 GHz, with at least 40 dB image rejection over the entire DC-coupled 1+ GHz bandwidth. Signal chains such as this are central to many applications, for example, wideband 5G receivers, high data rate microwave backhaul links, software-defined radios and radar, and wideband digital predistort or DPD power amplifiers. The signal chain we will look at today will utilize the LTC5594 IQ demodulator driving an AD9208 3 gigasample per second 14-bit dual ADC. A key benefit of the LTC5594 is its high demodulation accuracy. This IQ demodulator has SPI register programmability for minimizing or nulling out the two most troublesome demodulator impairments, which are DC offset and image response. It's very desirable to null these impairments immediately, right at the source of the error, as we do here. In this way, we maximize headroom and reduce the amplitude of the spurious products that could be generated downstream. The LTC5594 also has provision for certain other high-order nonlinearities to be minimized, namely baseband IM2, HD2, IM3, and HD3. These unwanted products are already quite low, typically -60 dBc or better. But if desired, they can also be nulled even lower. For receiver applications, improved demodulation accuracy means more complex modulation can be processed, and ultimately higher data throughput. And for DPD applications, improved demodulation accuracy means a more accurate PA output signal is possible, also supporting more complex modulation schemes with very low EVM, or error vector magnitude. Because of the LTC5594's high image rejection and low DC error, another immediate benefit is reduced FPGA resources. There is no need for quadrature error correction or DC error correction in the FPGA. Demodulator calibration need only occur once, and then the register values are typically saved in non-volatile memory. Calibration holds relatively well with respect to temperature, as documented in the device datasheet. Next, let's take a look at the detailed design. The LTC5594 has a single-ended 50 ohm, 500 MHz to 9 GHz RF input. Only one shunt matching capacitor is necessary. The LO input is almost as simple. The device has internal LO matching to reduce quadrature phase errors due to LO harmonic content. Be sure to set the LO registers for your LO frequency in accordance with the datasheet recommendation. When using the device up at the higher LO frequencies, best performance is obtained by driving the LO up near the higher end of the recommended LO power range. For the interstage filter, we will be using external third-order low-pass filters on the PC board. These simple filters attenuate LO leakage, which reduces output spurious products and improves dynamic range of the amplifiers. The LTC5594 output amplifiers are ideally suited for driving wideband, high-resolution ADCs. The gain is digitally adjustable from 8 to 15 dB and 1 dB steps, which is useful for finding that perfect balance between sensitivity and linearity. For list design, we will include a fifth-order external anti-alias filter before each ADC. This filter is also important for reducing LO and LO harmonic leakage into the ADC, which could otherwise fold back from a higher Nyquist zone and show up in the middle of the passband. The Adc driver circuitry can be simple, as we see here. The capacitors help reduce the input impedance reactive component and also provide additional low-pass filtering. Next, let's go to the lab and observe actual performance. Here we see the LTC5594 device with an RF input, an LO input, and the baseband differential outputs, directly driving the AD9208. The 3 GHz ADC sample clock is supplied externally. The JESD204B reference clock is also supplied externally. The AD9208 includes many helpful built-in DSP functions, such as decimation filtering. We will enable HB1, a half-band FIR filter, to ease the external anti-alias filter requirement and reduce data rate over the JESD204B interface. The IQ demodulator is simple to configure. It's especially important to choose the correct LO frequency settings. The same window is where we null out the DC errors. For faster results, the I and Q can be nulled separately in the time domain. When we switch to the frequency domain, the DC component will be minimized. Also on the same window is where we can null the image response. Quadrature gain and phase are adjusted separately. Next, we sweep the frequency response and image rejection. For best image rejection across the 1 GHz bandwidth, it's important that the I channel and Q channel delays be precisely matched. In this case, we see the desired response output flatness is within about 1 dB peak to peak, with image rejection of about 43 dB or better. Beyond 1.4 GHz bandwidth, steep roll-off exists thanks to the ADC's internal HB1 filter. Now let's look at linearity. 2 RF tones are applied. We begin by nulling IM2. HD2, IM3, and HD3 are nulled in the same manner. And when complete, the waveform should look like this. For best results, we'll do one more DC offset null. And one more final sweep test to validate the frequency response and image rejection. And that's it. Our IQ demodulator is fully calibrated. We can demodulate over 1 GHz bandwidth with image rejection. In conclusion, the LTC5594 can address many ultra-wide bandwidth needs and solves the difficult-to-manage image and DC offset problems, which can reduce the need for FPGA resources. By calibrating out demodulator impairments, many of the historical problems associated with direct conversion architectures are reduced or eliminated. System performance improves, supporting the more complex 5G modulation schemes. For demodulating up at higher microwave frequencies, such as Ka band, Analog Devices offers a multitude of microwave downconverter products to choose from. For detailed schematic and test results, please refer to the LTC5594 datasheet on our website. For applications assistance or for more information, please call or visit analog.com. Thank you for watching.